Hello guys, this video is going to be the first of the 3 video series tutorial for the fluid mechanics course, which is KMK20103. For this video, I'm planning to spend about half an hour to solve for both questions in our quiz number 3, which already been done during our week 9 lectures. So, I'm going to start with the question number 1. In the enlargement shown in figure 1 below, the pressure at the point A is 176.5 kilopascal, and then the pressure in the point B is 194 kilopascal. By assuming no energy losses, the keyword over here is no energy losses, meaning that the HL was actually equals to 0. Calculate the volume flow rate of the oil. Volume flow rate is represented by the symbol Q. Given that the specific weight of the oil is 8.829 kilonewtons per meter cubes. And of course, specific weight from chapter number 1 represented by the symbol gamma. The question is asking for what is the value of Q. And then, if you notice that, it doesn't mention that the Q, you need to find either QA or QB. It is because from the chapter number 5, we do know that the flow rates at the point A was actually equals to the flow rates at the point B. So, it doesn't matter either you're going to find QA or QB. Either one should be the same answer. So, I'm going to start this question by writing down my Bernoulli's equation. So, I will say that Bernoulli's equation, pressure at the point A over rho G plus ZA plus VA squared over 2G, it is actually equals to pressure at the point B over rho G plus ZB plus VB squared over 2G. So this is my Bernoulli's equation, and again, if you notice that in the question it does mention about the no energy losses due to friction. Therefore, in the term over here, we don't have the term HL because we just simply assume it is equal to 0. And then, I'm going to say that obviously, if you notice that at the point A and point B here, it is actually at the same elevation. So, if I'm going to draw my pipes, it looks something like this. So this is going to be my point A, this is going to be my point B, and then let's say this is my reference point. The heights of the point A are actually equals to the heights at the point B, or I can say that the potential energy at the point A was actually equals to potential energy at the point B, because by definition, potential energy equals to mass multiplied by gravitational acceleration multiplied by Z, which is elevation. So this one is going to be ZA, this one is going to be ZB. Therefore, in this case, I can cancel out my ZA and ZB. So in here, I'm going to write down something like this, because I did know that from the diagrams, ZA was actually equals to ZB because it is a horizontal pipes. It is quite funny because if you notice that if you are comparing this question together with our test 2 question, question number 1B, actually I'm using the same information as this one, except that for the test question, actually I'm rotating this pipe, meaning that previously the pipe looked something like this, and then what happened in the test is I'm rotating this pipe, make it look something like this, while all the answer informations are the same. For example, the oil with the same specific weight, and then it was flowing from the point A to the point B. All the information are same, except that the ZA here for the test is not equals to ZB, because obviously from the diagram here, you should notice that this is my point B, this is my point A. Let's say this is my reference point. The heights of the point A are not equals to the height of the point B. Therefore, I cannot just say, oh, ZA equal to ZB because it looks the same as the quiz question. It is wrong, yeah, because we have to understand the concept of potential energy. So now I already cancel out my ZA and ZB here. So now I left out with PA minus PB. I'm going to rearrange everything. Divided by rho multiplied by G equals to VB power of 2 minus VA power of 2 divided by 2G. What else information is given? In the question, it just mentions that the pressure at the point A is 176.5 kilopascal. Therefore, I can just simply substitute into this equation. This one is given, which is 176.5 kilopascal. And then, what else? The point B is 194.4. So the PB over here is 194.4 kilopascal minus, how about rho and G? From chapter 1, I do know that rho is actually a density. And then rho multiplied by G is actually referring to the specific weight. So I can say that rho is density, while gamma is actually equals to rho multiplied by G, which is equals to specific weight. Therefore, and again, the specific weight was actually given in the question here. Given that the specific weight of the oil is 8.829 kilonewton per meter cube. So I'm going to say that my rho multiplied by G is actually 8.829 kilonewton per meter cube. From the unit conversion over here, I mean from the units, from the given unit for the pressure and also for the specific weight here, I noticed that both are actually in the unit of kilopascal. You have to note that for the kilopascal is not a basic unit. Just like, for example, let's say I have a question for the HL, given that the length of the pipes is 2 kilometers, for example. So obviously, if I want to find, let's say I want to find HL equals to F multiplied by L over D multiplied by V squared over 2G, we have to make sure that all the units are in the basic unit. In this case, the length or the L over here was 2 kilometers. I cannot just simply substitute into here, but instead I need to convert from kilometers to meters. Therefore, I'm going to say that the L equals to 2000 meters. So same goes here. So because it was in the kilopascal, therefore I'm going to convert to pascal. 176.5 times 10 to power of 3 minus 194.4 times 10 to power of 3 with the unit pascal divided by, and again this one is a kilonewton, therefore I need to convert to newton. 8.829 multiplied by 10 to power of 3 newton per meter power of 3. So once I divide both, I'm going to get a value of in the unit of meters. So let me calculate it for you. Wait a second. Let's say a value was something. I'm going to put a random value. 800 meters. Make it 8 meters. Actually, I can prove why the pascal divided by newton per meter cube is going to be end up with the meters. So let's check here. Pascal is actually a unit of pressure, And then I do know that the pressure was actually equals to force divided by area. And then the force, Newton's third law, m multiplied by acceleration divided by area, which is m power of 2. And then mass, unit of kg, multiplied by acceleration, which is unit of meter per second power of 2, divided by meter power of 2. So the Pascal is actually equal to kilograms per meter second square. So this is unit for pressure, and then I can check also for the unit of specific weight, which is Newton per meter cubes. The unit for specific weight is actually Newton per meter cube. Newton is unit of force. Force equals to m mass multiplied with the acceleration divided by meter power of 3. Mass multiplied by acceleration is just equals to this one, kilograms per meter second square divided by meter power of 3. So I'm going to end up with kilograms meter second square multiplied by 1 over meter power of 3, meter and meter power of 2. So now I end up with the unit of kilograms meter power of 2 per second square. So divided by these two, I'm going to end up with the unit of meter. So yeah, this is correct. But then don't worry much about the unit, because this one is just I'm just proving to you how do I end up with the unit of meters, because all the terms in the Bernoulli's equation was actually with the unit of meter, which is meaning that the meters of energy. Alright, so let's say once I solve for this one, let's say I'm getting a value of 3.45, and then it's actually equals to, on the left side, I have V power of 2 minus A VA power of 2 divided by 2G. So I got one equation here. If you notice that here I have VB and then I have VA, meaning that I'm going to have two unknown. I didn't know what is the value of VA. I also didn't know what is the value of VB. So by knowing only one equation, which is equation number 1, but I have two different unknown, I cannot really solve this one, meaning that I need another equation to solve it. Just like example I gave you in the class. Let's say I have one equation, A plus B equals to 10. One equation. And then I'm going to ask, during the class I did ask you, what is the value of A? You cannot really have any value of A. Why? Because we have two unknown, A and B. But we only have one equation. I cannot really solve it because A can be anything. A can be 5, A can be 2, A can be in fact negative value. So in order for me to solve for this one, I need another equation. Same principle is actually applying to here, because in here I got two unknown, BA and also VB, but I only have one equation. Therefore I cannot really solve this one, regardless either you doing something like this. I did notice that some of you are doing something like this. 3.45 multiplied by 2 multiplied by G, and then VB power of 2 minus VA power of 2 equals to this one. And then they say that okay, VB equals to, let's say this value equals to 5 plus VA power of 2 and then square. You still cannot solve it because you have two unknown but only one equation. Therefore you require another equation. Obviously, because the fluid was moving, in addition to the Bernoulli's equation here, we can also apply for the continuity equation, because continuity equation is derived from the principle of conservation of mass. I can say that area at the point A multiplied by velocity at the point A equals to area at the point B multiplied by velocity at the point B. Area at the point A, given the diameters, was 125 and 250. Therefore, I can calculate for the area at the point A, which is pi, multiplied by 0.125 power of 2 divided by 4, multiplied by VA equals to pi 0.25 power of 2 divided by 4 equals to VB. Both sides I have pi over 4, so I can cancel out because the operation here is multiplication. And then I can say that my VA is actually equals to 0.25 power of 2 divided by 0.125 power of 2 multiplied by VB. I solve this one, then I'm going to get VA equals to 4 multiplied by VB. So this is my another equation which is in the form of VA and VB. And then going back to here, because now I already have two different equations, therefore I can solve it because I can just simply substitute VA into this equation. Then I'm going to get one term only instead of VA and VB. Now I'm going to end up with a single term. So what I'm saying here is, before this, I do get, hold on, yeah. I have VB power of 2 minus VA power of 2 divided by 2G is actually equals to PA minus PB over rho G. But then I also know that rho multiplied by G is equal to gamma. So I can also rewrite here as VB power of 2 minus VA power of 2 divided by 2G equals to PA minus PB over gamma of the oil. And then PA equals to 176.5 power of 3 minus 194.4 times 10 to power of 3. I will explain why times power of 3. 8.829 times 10 to power of 3. And then I should get the value of something. And then I also know that from continuity equation that VA equals to 4 multiplied by VB. Therefore, I can substitute into here. So I end up with VB minus 4 multiplied by VB power of 2 divided by 2G equals to this value. And then 1 minus this one you have to be a little bit careful, yeah, because here some students are saying that VB power of 2, and then they're replacing it with this one, VA equals to 4 multiplied by VB, which is correct. And then they say that VB power of 2 minus 4 VB power of 2, which is incorrect, because if you notice that the bracket here, the power of 2 here is for the whole terms, meaning that 4 power of 2 VB power of 2. So the correct answer should be VB power of 2 minus 4 power of 2 is going to be 16. VB power of 2, VB minus 16 is going to be negative 15 VB power of 2. Then you can actually solve for VB, because now we only have one equation, one unknown, which is VB. But then the VA already cancelled out because we replace it with another equation. So this is the example on how to apply the Bernoulli's equation together with the continuity equation. As I keep on mentioning about the Bernoulli's equation and continuity equation, it is applicable as long as the fluid, for example, the oil, was actually flowing from one point to another. So we can always applying it. So this one should be straightforward, yeah. And of course, some of you are actually confusing between specific weight, which is gamma, together with the density. This one you cannot make a mistake, because this one is so basic, which is covered in our chapter number 1. So for example, here they're saying that specific weight of the oil, obviously it was referring to the gamma, and then the gamma was actually equal to rho multiplied by G from the Bernoulli's equation. So now I'm going to move into the question number 2. The ventrimeter shown in the figure 2 carries oil with the specific gravity of 0.9. The specific gravity of the gauge fluid in the manometers is 1.40. Given that the volumetric flow rate of the oil is 1.14 times 10 to the power of negative 2 meter cube per second, and assuming no energy losses due to frictions, calculate the height of the manometers H over here. Alright, let's take a look at the diagram first. If you notice that inside here we have oil, correct? We have oil actually flowing from the point A over here to the point B. It's not. It doesn't mean that the oil start to flow from point A and point B. Actually, we're interested between point A and point B, and definitely, the oil was actually traveling, and then it will pass through point A, and then it was passed through point B, and then coming out to the pipes in the end of the pipe over here. So, but then we interested with only point A and point B. So, because the oil was actually flowing, as I said before, we can always apply the Bernoulli's equation between point A and point B together with the continuity equation between point A and point B. So, if I'm going to write down my Bernoulli's equation between point A and point B here, I'm going to get something like this. PA over gamma of the oil plus ZA plus VA squared over 2G equals to PB over gamma of the oil plus ZB plus VB squared over 2G. And obviously, ZA is not equal to ZB, but instead, the height difference between point A and point B was actually ZB minus ZA equals to 0.25, because point B here are higher compared to the point A. Therefore, point B will have higher potential energy. What's the value? The value is height difference between A and B, which is 0.25. So, what I can do here is I can solve for the ZA and ZB. What I'm saying here is, if I'm going to rearrange it, I can rearrange, look something like this. I have PA minus PB divided by gamma of the oil equals to, I'm going to move this to the other side because this one has been moved to the side. So now I have ZB minus ZA plus VB squared minus VA squared over 2G. Okay, let us check our terms. We didn't know what is the value of PA. We also didn't know what is the value of PB because it was not given in the question. Gamma of the oil can be calculated because specific gravity equals to 0.9. Therefore, the density of the oil is going to be 0.9 multiplied by 1000 is going to be 900 kilograms per meter cube. Therefore, the specific weight of the oil equals to 900 multiplied by 9.81 because specific gravity equals to rho multiplied by G. So I can calculate this one. So the unknown here I have PA and also PB, but then the ZA and ZB can be calculated, which is okay. And then I have VA and also VB, which is unknown. But if you notice that in the question here, they gave me here, this is a statement. Given that the volumetric flow rate of the oil is 1.14 times 10 to the power of negative 2. What does it mean? It means that it was given in the question the volumetric flow rate, or the Q, equals to 1.14 times 10 to power of negative 2 meter cube per second. And also, you should note that what is Q? Q is actually equals to area multiplied by velocity. How about the area? Area, as long as the diameter is given, because usually the pipe we assume is a circular pipes. As long as the area is given, the diameter is given, area always can be calculated. Therefore, I can say that given the Q was actually equals to A multiplied by V equals to 1.14 times 10 to power of negative 2 meter cube per second. I can always calculate for my VB and also my VA. Why? Because Q equals to A multiplied by V. As long as I know the area, the velocity always can be calculated. For example, the VA equals to Q at the point A divided by area at the point A. Q at the point A was actually the same, yeah? Q always the same. 1.14 times 10 to power of negative 2 divided by area at the point A, which is pi, multiplied by the diameters, which is 200 millimeters or 0.2 meters divided by 4. Then I'm going to get the value of VA in the unit of meter per second. Same goes for the VB. VB equals to Q at the point B divided by area at the point B. The area is actually pi multiplied by diameters power of 2 divided by 4. So, and if you notice that the Q here was actually equal to 1.14 times 10 to the power of negative 2 divided by pi, converted unit to meters, 0.075 divided by 4. Then I'm going to get the velocity at the point B. Then I can solve for this one, right? Because before this, I have so many unknown. For example, in the beginning, I don't have the PA, I don't have the PB, I don't have the VA, and I also don't have the VB. So I try to reduce as much as unknown as possible. So meaning that otherwise I cannot really solve it because I have so many unknown. I have PA, I didn't know what is the value of PA, PB is not given. Same goes for the VB and also VA. Velocity at the point A and point B is not given. But instead, they gave me the flow rate. So theoretically, I assume that everybody should know that the flow rate are always the same inside the pipe. So meaning that if the flow rate of oil entering into the pipe was 10 meter cube per second, so at any given point, the flow rate are always the same. But the velocity is not necessarily the same because VA is not equal to VB. Why? Because V is actually depending on the area. The smaller the area, the higher the velocity. So once I find the value of VB and VA, actually I can solve for PA and PB. So I'm going to put a value. For example, here I have PA minus PB divided by rho multiplied by G, 9.81 equals to ZB minus ZA. From the diagram, I should know that 0.25 equals to 0.25 plus, I need to solve for VA and VB. So I'm going to calculate for VA and VB. I should get VA equals to 0.393. VB equals to 2.58. So then I'm going to substitute into the Bernoulli's equation here. I have VB, which is 2.58 power of 2 minus 0.363 power of 2 divided by 2 multiplied by 9.81. So actually I can solve this one, meaning that I have to solve the term here first, and then I can equalize to this one. Then I can get what is my PA minus PB. Means that this is the value of pressure difference between point A and also point B. So let's say I've got the value of, I just put random value, 5,100 Pascal. So now I already got the value of the pressure difference between point A and point B by using Bernoulli's equation. Going back to the same diagram over here, the question is actually asking for what is the H over here. What is the value of H? Meaning that what is the value of manometer deflection over here. So first of all, before this we already got, right, PA minus PB. PA minus PB equal to 5,100. This is rounded numbers, yeah. I just put a value over here. So you should ask yourself, we already solved for this part. How about this part? This part is what we call manometers. And then you should ask yourself, what is the function of manometers? From chapter number 2, we did learn about the manometers, because the function of the manometers here is actually to measure the pressure difference between 2 points. Meaning that these manometers was actually to measure the pressure difference between point A and also point B. So by applying the manometer concept, I actually can solve for the value of H, because here the question asking for what is the value of H. So what I'm going to do here, I'm going to label it here. First, I'm going to label point 1. Here is going to be my point 2. And of course, this one is going to be my point A. This one is going to be my point B. And then I'm going to apply the principle of fluid statics. Usually I'm going to I love to use to understand the concept of fluid statics. Usually I love to use the example of scuba diving. Yeah, imagine that you're going for a scuba diving. So this is initially you at the surface of the sea water. So it's as you go deeper, you will notice that you will feel the pain on your ears and your bodies, because the sea water here is going to apply a pressure on your body. That's why usually if you go for the scuba diving, you will require a special suit, because it has to withstand the pressure exerted by the sea water. Meaning that the deeper you go, the higher the pressure. So applying that concept, I can say that between point 1 and point A here, the pressure, not potential energy, but the pressure. The pressure at the point 1 is actually higher compared to the pressure at the point A, because the deeper I go, the higher the pressure. And then I can say that P1 minus PA, the difference in pressure between point 1 and the point A equals to rho, it was filled with water, oil, rho of the oil multiplied by G multiplied by H. In this case, the height difference between point 1 to the point A here was actually equals to H. See, from here to here was H. Let's say this one is a Y, it's a X. H plus X. So now I'm going to say that P1 minus PA equals to rho multiplied by G. Let's use as gamma. Gamma of the oil multiplied by H plus X. This is going to be my first equation, or I can rearrange it to make it nicer. P1 equals to PA plus gamma of the oil H plus X. This is going to be my equation number 1. What I'm doing here is I'm measuring the pressure difference between point 1 and point A by using a manometer concept. And then I also can calculate what is the pressure difference between point 1 and also point 2. So I'm going to say that P1 minus P2 equals to gamma of the fluids multiplied by the h. In this case, the h was the height difference. In this case, coincidentally, the height difference was actually h. Therefore, I can just use h over here. How about the gamma of the fluid? In here, it's stated that here the specific gravity of the gauge fluid in the manometer was Sg of the fluid was actually equal to 1.4. Therefore, the density of the fluid was actually equal to 1.4 multiplied by 1000 equals to 1400 kilograms per meter cubes, the density. Therefore, I can say that here is going to be 1400 multiplied by 9.81 because gamma equals to rho multiplied by g, but then I already got the rho from the specific gravity, because I also know that specific gravity of the fluid equals to density of the fluid divided by density of water. In this case, density of water always equals to, we assume equals to 1000 kilograms per meter cube. Then I'm going to get the value of h. This one is going to be my equation number 2. And also, I can calculate the pressure difference between point number 2 and also point B. So it's going to be P2 minus PB equals to, it was filled with the oil. Therefore, it's going to be gamma of the oil multiplied by the, what is the height difference between point 2 and point B is going to be, from here to here is going to be x, from here to here is going to be 0.25. So I'm going to write down as x plus 0.25. So rearrange it, I'm going to get P2 equals to PB plus gamma of the oil multiplied by x plus 0.25. So let's name it as equation number 3. So now I'm going to substitute equation 1 and equation 3 into equation number 2. So now I have equation 1, which is P1. I'm going to replace it into here. So now I'm going to end up with PA plus gamma of the oil H plus X minus P2. In this case, the P2 was equation number 3 minus PB minus gamma of the oil X plus 0.25 equals to gamma of the fluid. Gamma of the fluid multiplied by H. Alright, so I'm going to extend it so that easier for me to cancel out the same terms here. So now I have PA plus H, gamma of the oil, plus X, gamma of the oil, minus PB, minus gamma of the oil multiplied by X, X gamma of the oil, minus 0.25 gamma of the oil. 0.25 gamma of the oil equals to gamma of the fluid multiplied by H. So let's check out any same term. Here I got plus gamma of the oil. Here I got minus gamma of the oil. One is plus, one is minus. I can cancel out this one. What else? Does it? Hold on, yeah. Let me check it first. H plus X. Yeah. Okay. So now, if you notice that before this, I assume that. If you notice that based on this diagram, I assume that the height difference between this point, this area, these manometers was actually 0.x. But then now I don't have I don't have any more x over here, which is good because usually the x is an assumed value. We cannot have any value for the whatever we assume the x is. Therefore now I don't have x anymore. Therefore I can rearrange this one. So I'm going to rearrange again. So now I'm going to end up with PA minus PB equals to, so this one should be moved to the side. So now I have H, gamma of the fluid minus H, gamma of the oil. This one is going to be positive. This one I'm going to move this side. It's going to be plus 0.025 gamma of the oil. Can I really solve it? Yes, because before this, if you remember, I'm using the Bernoulli's equation to find the pressure difference between point A and point B, which is PA minus PB equal to 5,100. Therefore, this one is actually equal to 5,100. So let's check the term here. The H is unknown, but then the gamma of the fluid and gamma of the oil can be calculated. Therefore, actually I can solve for this one. Therefore, I'm going to rewrite here as H. I'm going to take out the H. So now I'm going to end up with gamma of the fluid minus gamma of the oil plus 0.25 gamma of the oil equal to 5,100. Therefore, my H is actually equals to 5,100 minus 0.25 gamma of the oil divided by gamma of the fluids minus gamma of the oil. Then I can solve for the H over here. So this question is good, which is usually how the final exam look like. Why? Because this one is a combination of both, meaning that first we have to understand that this is the manometers. This area is the manometers, and then you should ask yourself, just like during our lab session, what is the function of manometers? Manometers was actually to measure the pressure difference, meaning that in this case, this manometers was actually to measure the pressure difference between point A and also point B. Why the pressure difference is important? Because for the fluid to flow, pressure difference does influence the flow of the fluid. For example, in this case, I'm going to apply the Bernoulli's equation. If you remember this one, and then ZA, BB, rearrange it, I'm going to get PA minus PB over gamma of the oil equals to ZB minus ZA plus BB squared minus BA squared. And then the pressure difference here was actually important because sometimes let's say the question asking for pressure difference, sometimes I can use the manometer to find the pressure difference. And I also noticed that during our quiz number 3, one of your friend is actually referring to the something what he did during the lab session, which is good because at least you understand what's the difference between the lab session and the question over here. What your friend did during the quiz is he showed me the answer, and then they said that they are using the Bernoulli's equation to find the PA and minus PB. For example, let's say what he did over here was first they started with the Bernoulli's equation, something like this. And then they solve for the PA minus PB, just like I showed you before. Let's say they get the value of 5,000. And then what he did over here is once he got PA minus PB equal to 5,000, then they say that rho multiplied by G multiplied by H equals to 5,000. The H over here was actually the height difference between this point. Because why? Because he still remember during the lab session, to find the pressure difference, we are going to apply the rho multiplied by G multiplied by H, for example, for the pitot tube in the experiment number 5. So they are saying that okay, pressure difference between point A and point B was actually equals to rho multiplied by G multiplied by H. It is incorrect. The reason why it's not this simple is because if you notice that during our lab we have water flowing inside the pipe. At the same time, for our manometers here, we're also going to have water. That's why for the lab, we can use this equation, meaning that to find the pressure difference between this point, and just simply use rho of water multiplied by G multiplied by height difference here. Because both inside the pipe and also inside the manometers are using the same fluid, which is water. But then for these cases, if you notice, this is the oil. The yellow one is oil, and then for the manometers, they fill with the manometer fluid with the density of 1400, while for water the density was actually 900. So both liquid are having different density, therefore you cannot use the same methods in the lab to solve for the question. Instead, you have to use it. You have to calculate in individually. I think most of you are a little bit struggle with the how to calculate the pressure difference between inside the manometers, which is you already covered for quite some time in your chapter number 2. And also, someone may ask, how do I know which point to select? Meaning that this one definitely is going to be point A, this one definitely is going to point B. How do I know which point to select? I cannot just simply select over here. Let's say I want to name it here as a point 1, and then I want to name it here as a point 2. It doesn't make any sense. Why? Because if I want to calculate pressure difference between point 1 and point A, you should ask yourself, because from here to here it was filled with the manometer fluid, but then in here to here it was filled with the oil. So if you want to calculate pressure difference between point 1, P1 minus PA, it should be density multiplied by G multiplied by H. If you're going to select the point 1 over here, which density are you going to use? Because in here obviously it was manometer fluid, or let's say a mercury, and then after some time it was filled with the oil. Then you should ask yourself which density you want to use. That's why usually to select the point, you have to make sure that the density are the same. For example, this one was filled with the oil up to this point, therefore I can name it here as a point 1. From here up to this point, it was filled with the same fluid, mercury, so I can name it here as a point number 2. So to calculate the pressure difference between point 1 and also point A, I can use rho, it was filled with the oil, multiplied by rho of the oil multiplied by G, and then I need to calculate what is the height difference between point A and also point 1. To calculate the pressure height difference, I should move from here. I will move upwards up to this point. So it was labeled in the diagram, it was H. Therefore, I'm going to write as H. But then I still have another distance from here to here. It doesn't label, therefore I'm going to say that, okay, let's label it as a point X. Let's assume that the heights between this point and this point was X. So it's going to be H plus X. So that's why I end up with P1 minus PA equals to rho of the oil multiplied by G multiplied by H plus X. So rearrange it, I'm going to have P1 equals to PA plus rho of the oil multiplied by G multiplied by H plus X is going to be equation number 1. So for equation number 2 should be straightforward. P1 minus P2. Between point 1 and point 2, it was filled with the mercury. Therefore, I'm going to say that rho of the fluid or rho of the mercury multiplied by G multiplied by H. So I can name it as the equation number 2, and then for the P2 minus PB is actually equal to the distance between this point to the point B over here. But then from here to here was 0.25, but then this area is unknown, so we assume equals to X before. Therefore, I can say that rho of the oil multiplied by G multiplied by 0.25 plus X. If you do the further studies for the subject, you'll notice that actually question 1 and question 2 is quite similar in general. Why? Because in the question number 1 here, the pressure is given. See, the pressure is given in the question. But in the question number 2 here, it's quite similar because I still need to find the pressure. But instead of finding the pressure by using the information given, instead sometimes I have to use the manometers to solve for the pressure. Once I solve for the pressure, I'm going back to the Bernoulli's equation, which is look something like this. So this subject is a pure engineering subject. Therefore, it is required a high understanding of the concepts, because if you notice that there's not so many equation, we have to remember just a couple of equation. Bernoulli's equation, Darcy, continuity, and etc. I think I already spent about half an hour for this video, so I'm going to stop for this one. I'm going to continue for the second video, which is covering on the serial pipeline system. I will select one question and then followed by the third video, which is on the parallel pipeline system. I hope this video will help you to have a better understanding for the subjects. Thank you.